Hello, welcome back. In this lecture, I will show you how to solve a Hit equation in Junior, and there's no inverse modeling in this course, so if you already know how to solve a PDE numerically in any languages, you can just skip this video. And let's recap a little bit about the discretization form for this Hit equation. And in the next lecture, we see how we can arrive at a linear system by discretizing the PDEs using appropriate finite difference schemes, and also how to discretize the directional boundary condition and Neumann boundary conditions. Okay, let's start from here, where we already have a linear system to solve. And this is a solution vector, and this matrix A, and B depends on kappa, which is the diffusivity coefficient. So let's do something here. First, we need to specify some parameters for the discretization. Let's discretize our domain into 50 equal spaced subintervals, and so we specify n equal 50. And let's think about the simulation. Let's also do 50 step, and so we have 50. We have actually 51 nodes spatially and 51 nodes temporally. So our solution vector will be, it's actually a vector, but we just concatenate all the vectors from each time into a single vector, and that will be n plus 1 and n plus 1. And we already know that the first step are all equal to 0, so because of I just made a 0 matrix, so it's okay to just skip assigning the initial conditions. So let's create this matrix A. So let's first create a kappa, and the kappa equal, and we need this x here. So x is the coordinate for each index, and here it is from 0 to n times what is delta x. Delta x is just 1 over n, and is delta x. Okay, so what's kappa? And the kappa is our A and B. A is, maybe I can just assign some numbers. A equal 5.0 and B equal 2. And so our kappa is A plus B times x. Okay, so let's assemble this matrix. So let's first calculate lambda. So what's lambda? Lambda is just a kappa times delta t. And delta t is not defined, so we define delta t equal 1 over n m, and the kappa is just delta t over delta x squared. Okay, so we already done all the job here, or specifying all the parameters. Okay, so let us just assign all the f equal to 1. So we can just compute f. F is a vector, and actually we can also do the same. We just stack all the f together into a single vector. So we have, for each f we have this n vector, and we also have m time step because we start from time step 1 instead of 0. So it's actually once because we let f be to be 1 everywhere times delta t. Okay, this is what our f is. Okay, so the next step is to assemble this A matrix. Note A is a sparse matrix. Of course, you can just create a matrix and just do iterations and then create each entries. And actually, we can just go directly to sparse matrix. So we use sparse arrays, which is the sparse linear algebra library in Junior, and we create this A matrix, spot diagram, and the spot diagram is just It's just a function in sparse arrays to create a sparse matrix. And you can see the syntax here is just like you specify the corresponding diagonal and give the diagonal a vector. So that means you have, for example, if you have 1, 2, 3, 4, if this is -1, you have 1, 2, 3, 4, 5 here. And if you have 4, 3, 2, 2, 1 at the diagonal 1, that means it's in the upper diagonal. And if it is equal to 0, then it is in the diagonal entries. So what do we have here? So we have, let's go from the bottom one. So this is -1. So, and that is minus lambda, because we start from 2 and we end at n. Okay, so what about the 0? So for 0 is 2 times lambda and plus 1. And because this is element wise element wise addition, you have to use dot here. And you also do not need multiplication here. They are just simply interpreted as multiplication. And you have upper diagonal. For upper diagonal, you remember that there's 2 here. So I just want to create a lambda up, which is lambda from 1 to n minus 1. But lambda up, the first entry should multiply by 2. So this is lambda up. So we create a matrix here. Yeah. So let's go. So this is just a matrix here. So let's just do a loop to calculate all the u here. So for k equal 1 to m, because we have m steps. And so for each step is u k plus 1 equal a backslash u k plus f k. Yeah, we do not need a k plus 1 because when we write this f, we think the first column corresponds to the second time step. And okay, so then we just calculate all the u here. So let's execute this file. To execute this, let's go to this directory. And to execute a file, you just include this file. Let's see. Oh, yeah, because this is element-wise addition, so you have to use dot. Let's see what's this lambda. Oh, okay. Yeah, this is actually. Yeah, because here lambda, because here x is just a range, and so all the variables here are interpreted as a range. So we first convert it to array. Let's see. So yeah, what's a here? Mismatch. So what's the size of u? Size of u is n, and the size of f is also n. And what about the size of a? Oh, size of a is n plus 1. Okay, yeah, I made a mistake here. And what's n here? So this should be 1 to n instead of from 1 to n, because we have the size of lambda itself is actually n plus 1. And let's say if I miss, yeah. Okay, yeah, I get this u. Okay, we want to plot out the the temperature on the left hand side because we place a sensor here. So we use a plotting tool. Yeah, they have PyPlot or Plot or Plotly and a lot of packages here. So we use PyPlot here, and yeah, because there's some issue with my Mac, so I have to do something like this. But you do not need to do that. This is because my computer has some problem with that. Okay, so we plot U on the left hand side because the first entry is the left, and we plot all the time step. And yeah, and let's save this figure to save temperature. Okay, let's execute it again. Okay, let's see this figure. Yeah, that's it.